Okay, thanks for still being here. I can be quite quick, I think, but I'm gonna just introduce QMod 3. And QMod 3 was a new category in this year's EMA. So I think we heard a little bit about it already, but the point was that Guillaume's group was able to generate around 8,000 models for the targets that were computationally feasible. And so the EMA task was, given these 8,000 models you have for the targets, are you now able to pick the top 5 out of these 8,000, and can you score them from 1 to 5? And so we can kind of have a threshold of at least analyzing 80% of the targets for us to then include the group in the assessment. And so we had around 20 groups submit more than 60 targets. And as a baseline, we decided to use essentially the internal baselines from Massifold, so the confidence scores that come from AlphaFold 2, IPTM, PTM, and PLDT. So then the idea here is that you'd have to either use this information in some substantially informative way or integrate some external information to do better than these internal based metric rankings. So the first task, though, was really to take these 8,000 models that we had from each of the Massifold data sets and score them against the experimental structure. And how we did that was using open structure, which we already heard about a few different times. And so here I'm just showing the example for, oh great, okay, yeah, I'm just showing the example for one of the heteromer targets. So with some of these scores from OpenStructure that we just heard about from Randy. And this is how the Massifold models in the data set for this target would rank if we look at different types of scores. And so you can see that for some of these especially, the distribution is quite flat. So there's a lot of models in this data set that are similar quality. And this is what we saw for a few actually of quite a few of the targets that we were looking at. So this is a monomer. So now we no longer have these interface-based scores. But the point is, again, the top 5 models here might not distinguish themselves significantly compared to the top 100 or even top 1,000, depending on the score that you look at. It's not always the case, though, so there are cases where the fall-off is a lot more abrupt. And so what we wanted to do when kind of assessing how well somebody had picked out the top 5, we wanted to make sure that we weren't overly penalizing somebody for picking, say, a model 100 and placing it as first in the example I showed just a second ago, but you might actually be penalizing for picking model 100 in this case. And so what we kind of converged to in terms of how to do this was a penalty-based initial processing of ranking. And so what this is to each predictor group, we assigned a penalty for a score type for every target. And what the penalty is, it's just the square difference between the score that that model has, the score that the first model has, for example, in the true ranking that we've calculated, versus the score that the model that somebody has put as their first has in the true compared to like the true scores that we know of. And then here we have I, so we're actually doing the sum between first all the way to 5th place. There is no further penalty for skipping a target. And so obviously here the best penalty you can possibly get is 0 penalty, where you've successfully identified the top 5 groups, but you don't get penalized for skipping one of the targets once you've hit that 80% mark. And then from this first step of processing, what we get is what I've called here a penalty matrix, which is essentially a matrix of penalties where each predictor group has a penalty for each score and for each target. So it turns out that it's actually quite interesting to do the analysis divided between monomers, homomers, and heteromers. And if we pull them all together, there's some interesting nuances that get diluted. So I'm just going to show the results into these 3 main categories. Now, The problem with these scores and with trying to combine these scores into a final ranking is the fact that you have to somehow decide how to weight these scores together, and also there's a lot of correlations between a number of these scores. And we see this, I'm just showing this 2 random examples here, but to show that we see this consistently both in the oligomers and in the monomer data sets where there's some scores that are highly correlated. So what we decided to do was, rather than actually trying to figure out a manual way of pooling these scores together and accounting for these correlations, we decided to actually find a systematic way of weighing these scores together based on the covariance of the scores within the data set that we're looking at. So what we actually ended up calculating is a weighted penalty, where the weighted penalty is essentially taking the score of penalties that for one target a predictor group has, given all the score types that we've actually assessed from OpenStructure, and we're weighting this vector by the covariance matrix of how these scores vary for the massive-fold models in that data set. So what that's going to do is essentially downweight the contributions of scores that are very highly correlated with each other into one. And so this weighted penalty now allows us to kind of collapse this vector of penalties to one penalty per predictor group per target, and then we assign a mean weighted penalty, a final weighted penalty per group, which is the mean across all the different targets. So there is an important detail that I want to mention, which is, I said that we're really using the covariance matrix of the scores to obtain these final weighted penalties, but we've already seen from Andri some of these nice yarn ball predictions that were present, especially from the V1 multimer versions that's run from AlphaFold 2. So we wanted to make sure that none of these particularly bad models were actually skewing the covariance matrix. And so we kind of had to find a way to prune these huge matrices. And what we decided to do was to use the Mahalanobis distance. If you haven't heard of it, the Mahalanobis distance is essentially a metric that will let you find the distance between a point and a distribution of points. So here we're considering how far any massive-fold model is scoring differently compared to the distribution of all massive-fold models in the data set that we're considering. And the idea is that this is quite useful because it's useful for identifying outliers when you're working with highly correlated variables and multivariate distributions, which is what we have here. And I think this is just to kind of show visually, compared to a more typical Euclidean distance, the Mahalanobis distance will be able to account for the correlation between two variables. Here I have x and y, so it will have effectively, in this case, a more elliptical outlier threshold that allows you to not consider some of these points as outliers. So what we did was we calculated the Mahalanobis distance for each of these massive-fold models compared to the set of monomers or homomers or heteromers, and then we rejected any of the models that were scoring with more than 3 standard deviations away from the distribution, and so this was the pruned covariance matrix that we used for weighted penalty calculation. This is just a point, but it's a kind of side point, but important point in terms of really trying not to skew with some particularly bad predictions the results for the rankings. So this is then the rankings split into the 3 categories that we have for these 3 for each predictor group. I'm not showing group names here because I want to make more of some 2 or 3 high-level observations. I think it's interesting that there's a significant number of groups that perform better than PLDDT and PTM and IPTM when it comes to monomers and homomers, but heteromers is quite difficult. So here we see that no one is really doing better than just looking at an IPTM-based metric from AlphaFold 2. And then the other interesting thing you'll notice is that there's not that much overlap between the top groups in the 3 different categories. And we noticed that there wasn't a huge jump between the top 5 groups and the ones that closely follow, so we decided to just compute these final rankings. So the way that we go from from the raw penalties to these final rankings, so how we combine all the scores, we decided to do a few flavors of this, some traditional z-scores based rankings and some rankings where we were essentially dividing up the covariances for each target. I think for the purpose of time, I'm not going to go through the details, but if anyone is interested. The point is that we ended up finding groups that were always robustly in the top 5, no matter these different flavors of ranking that we implemented. And so these groups I'm highlighting in red on the x-axis here. And for the monomers, today we're actually going to hear from 3 groups. I think the McGuffin group was already highlighted by Randy, also for standing out in QMod 1 and 2. And then I have the MI ensemble servers from Wei Zhang and David Shortle human. And what's interesting about these 2 groups is that not only do they light up in the monomer ranking, but if we do a very straightforward sum of the rankings across the 3 categories, these 2 groups are the ones that actually generalize the most. So they end up being at the top of this very simple global ranking. So I think there's something interesting in they perform well on monomers, and at the same time while not at the very top in the other categories, they end up being the ones that are at the top of a final ranking. So there's some general principle that's extrapolating well. And there are 2 quite different methods. We'll hear about them more later today, but David Shortle's method is actually much more based on some statistical observations just from a data set of high-resolution structures from the PDB and some physics-based potentials, whereas MI ensemble servers is relying on high-quality MSAs to find a really good reference model, and then from there having a quality assessment metric. So we have some indications, and we'll hear more later, about why they might be especially highlighted in performance for monomers. So the high-resolution data set was a single chain set of structures, so there's some skew there towards monomers, and we've corresponded with Wei Zhang's group, and they've highlighted that they expect essentially that the quality of the model that they end up picking will really affect how well they can then do quality assessment of other models, and this task for their method is much harder on complexes. But I think it will be interesting to hear a little bit more later, especially when it comes to the ability to then maybe generalize to other categories. The 2 groups that are robustly at the top are the top 2 for homomers, and they're both from Jianling's Chen's group from Multicom. We've already heard a little bit about Multicom earlier, but here we've got multiple LLM and Multicom human. And so my understanding is that these are both using some pairwise similarity metric, with the key difference that Multicom human is also incorporating the gate score. So there's some model similarity graph that's deep learning trained that is also adding to the information. And I think we'll have Pawan later tell us more about these 2 and their differences. So the final interesting observation here is that the heteromers, of course I haven't highlighted these, but we have IPTM from AlphaFold, and that's the top ranking. But then we have 2 robust groups that are again from the same group, and they're from Guzhen Zhang's lab. They're Guzhen Lab Human and Guzhen Lab Assembly. And here, from corresponding a little bit via email, the information I have is that Guzhen Lab Assembly is using IPTM. So this was a little bit my question, right? Like, are still the top groups here using some form of IPTM or PTM, and so ending up at the top, because essentially there's some leakage from the AlphaFold 2 metrics. But from my understanding, Guzhen Lab Assembly is using IPTM only for a preliminary screening, and actually Guzhen Lab Human should not be using PTM or IPTM or PLDPT at all. So maybe we'll hear more in the next session, but I think it could be interesting to understand if this is maybe an orthogonal method to AlphaFold 2 that's still head-to-head for heteromers from this perspective. And so I think that's pretty much it on my end. I have some final thoughts just on the EMA from this CASP. So we've heard from Randy about how these confidence estimates can actually help us understand and interpret experiments. So what is their utility further down the line? And so we've definitely seen that these finer grained atomic estimates add confidence and value in the model. So it might be interesting to consider whether this should be an explicit goal in CASP 17, which it wasn't this time around, so we were not actually doing any assessment on this metric. And the other interesting point of discussion maybe for later in the conference is the fact that from a practical experimental perspective, the confidence in the relative orientation of domains is very important. And so there's maybe something to be said about whether PAE matrices or some more general version of PAE matrices should be considered also as an evaluation category in CASP 17. For QMod 1 and 2, I have this, I think there was a nice slide that Randy showed from Gabriel where we have seen that there's been improvement in the overall scores for the top performing groups compared to CASP 15, so there's been some improvement there. And then for QMod 3, we still have this interesting observations that methods struggle to outperform AlphaFold 2 when it comes to big hetero complexes. So this is, I think, interesting. And there's something to be said for if we were to consider a future variant of QMod 3, maybe a full ranking rather than just a top 5 could be an interesting way of getting past some of the nuances that come with the underlying distribution of a set of models, which is what we had to deal with in terms of trying to assess altogether. So I think this is it. Thank you for sticking around, and if there are no questions, we can go for lunch.
Thank you so much, Alisia. Are there any questions? Because I know that anyone wants to go to lunch. So, good news is we will have a discussion session today at 6:40 p.m. And that will be a discussion session together for protein structure prediction and for quality assessment. And the assessors will be there. So if you have some urgent questions or not urgent at that time, so you can ask them at that time. So we will resume as we have it in the program at 2:45 p.m. with the talks from creators. And what else today holds for us? After that, we'll have afternoon poster session at 4:15, and then at 6 p.m. we'll have evening session where we have
the tape is up.
keynote speaker. Now we'll hear from David Baker at 6 p.m. and as I already told you,